So my agenda is about sensitivity, sharpness, depth of field, then a summary about the good news, the bad news, and what can be done. It's all about 2K, 4K, 8K, and aspects that relate to the use of these kind of cameras. So it's about images can be made in many sizes. On the left side you see an image of NHK. It has 133 million pixels, image diagonal of 44 millimeter. On the left there's a 2/3 inch imager, 11 millimeter. It's one of ours. Nowadays you'll find pixel sizes between 1.1 and 5 micrometer. Lenses stop down to 1.4 up to f11, f16. And in the broadcast arena, the definition for an HDTV camera is you have I call it 2K, even though it's not 2K but 1920. But the pixels are 5 micron. Sensitivity is defined at f11, 2000 lux. The 89.9% reflection of that well-known Kodak tile at 3200K. Sensitivities are some sensitivities about numbers. One of these days it was mentioned that the difference between 1920 and 2K is just 6.4%. But in the discussions, the sensitivities are at least over 100%. But what really does surprise me, nobody talks about 1080. Nobody wants to make it 1024 or any other number, even where the raster is much more. But this is just for the fun part. Now the real sensitivity. So we have a black body radiator. In this case, the left graph is at 3 color temperatures. There's a large formula. With that you can calculate the number of photons that fall on the pixel. The most important element of that formula that determines how many photons there are on the pixels is the pixel area. I call it in this formula the A cell. Exposure time, of course, 16.6 milliseconds in the P60 and 20 milliseconds for the P50. Scene illumination, as I said, normally it's 2000 lux. The reflection coefficient, f number of the lens, and then all the other elements. But now if you apply this to that default situation where nowadays HDTV cameras are specified at 2000 lux, the 89.9% reflection, 3200K f11, then with a 5 micron pixel and in a 16.6 millisecond integration time, you get about 3000 photons on the green pixel. About 3200 in red, and in blue it's about 1000. By the way, the reason why in 3200 you just don't have much blue. Blue is in the region of, if you look at the graph, somewhere between 400 and 480. And at that color temperature, you have more infrared, near infrared than you have blue. And surprisingly, people keep being surprised that blue is so noisy. Well, this is the reason why it's noisy. Well, now the sensitivity, number of photons in the pixel. First of all, it relates to the pixel area. The larger the area, the more photons you can collect. And the dimension of the pixel, in this case, I abbreviate it by h times h, where h is pointing to horizontal dimension. The other part is the f number of the lens. The more you open up the lens, the more photons you get. The more you close the lens, the lesser photons you get. And in essence, the sensitivity, the number of photons you get on your pixel, is a ratio between the width of the pixel and the f number squared. Noise, and Nowadays, many cameras are CMOS images, have CMOS images, especially if you go to 4K or 8K, because it's very difficult to obtain performance with CCDs. But because it's a CMOS imager, it means that the read noise is rather independent of frame rate, clock frequency, and these kind of things, where in the CCDs it would relate at least to the bandwidth and the square root of the bandwidth. So read noise is fixed, so I just treat it as fixed in this case. The other element with the noise is shot noise. That means when you have a gamma chart or you have illuminated parts in the image, you'll see also twinkling in it. That's a shot noise. Usually the read noise is only the noise you have in the blacks, in the dark, and the shot noise is the noise you get when there's more light falling on the pixel and it's photon generated, and it goes with the square of the outputs of the signal. So basically, the sensitivity, number of photons, and the noise together. Sensitivity, it scales like the square of the width of the pixel over the f number. You could also say, well, the width of the pixel is something like the diagonal divided by the resolution. But by the way, that square in the formula is only means that is proportional to, but I didn't have another symbol in the package. So you can also do it in a different way. And with this, where I made the purple circle, diagonal is something usually everybody knows, resolution is something everybody knows, and f number. Now, if you look at 3 dimensions of the pixel, 1.25 micrometer, that's when you have an 8K image in 2/3 inch, 2.5 micron, that's the nowadays available 4K imager, and for AC you have the 5 micron pixel. The first thing you'll note is that HD has a large range of f numbers in which the sensitivity is sufficient. And sufficient is in this case defined as I normalize it to 1. You can see it in the blue graph at f11 on the y-axis. You see the number is 1. Then you go to 4K. That means that because the pixel area is 4 times smaller and the dimension is 2 times smaller, it means that you have to stop down with your f number factor of 2. So we go to f5.6 to get the same amount of photons on the pixel, and with the same noise, it means that you get the same signal to noise ratio of 60 dB. But you already see that triangle, the red triangle which is made between the red curve and the purple line, is getting smaller. And then when you go to 8K, the 1.25 micron pixel, then you have only between 1.4 and 2.8 as a usable f number range that you can apply. Well, below 1, of course, you can use your camera with lesser light or by using larger f numbers. But in that case, you will have to need noise reducers, because actually the performance is not the raw performance of the pixel is not such that it can deliver what should be delivered. And when you are above 1, then usually that means that either you apply neutral density filters, or you can go down in light. Now, if you look at the graph, then what you see is, let's say that in HD you use it at f8, then you get equal number of photons in 4K when you use f4, and you get an equal number of photons in 8K when you would use it at f2. Sharpness. Actually, an imager is a 2-dimensional spatial sampler. The Nyquist frequency is just half the sample frequency, and actually the Nyquist frequency is the frequency up to which one can reconstruct a sample signal. On the left there is a table where in the column I have the image diagonal width of 8 mm, 11 mm up to 44. And on the horizontal, on the rows, you have 8K, 4K, 2K. And in that table, you can see how the pixel size changes. So as I said, when you have 2/13, that's 11 millimeter image diagonal. For 8K, you have 1.25 micrometer pixel width. In 4K, it's 2.5, and in 2K, it's 5 micron. And given the resolution, if you go to larger image diagonals, the pixel size increases. On the right side, I just quoted the Nyquist cutoff frequencies in line pairs per millimeter. Usually, it's more an optical measure. In our field, it's more appropriate, I think, to use TV lines or cycles per pixel width. But I thought let's try another unit. I don't see Larry Thorpe in the room, but this was a joke for him. You know that he is now with Canon. He introduced a very high sensitive camera. It's an HDTV camera, but then with a very, very large pixel. Now let's dwell a little bit on the MTF. The nice thing is, if you first of all let's look on diffraction. There's a formula. The formula reads MTF lens, and it's a simplified formula for calculating how the diffraction works of a lens as a function of f number and pixel width. And of course, pixel width translates in the end into an optical sample frequency. So as already stated before, when you go 2 f-stops down, when you go from 2K to 4K, and an additional 2 f-stops down from 4K to 8K, what you do then is you keep the ratio between f and h, you keep it a constant. So the nice thing and the surprising thing is that when you keep your sensitivity the same, then also your MTF at Nyquist stays the same. And that's also depicted in the graph with the blue dots. So on the x-axis you have the pixel width, 5 micron HD at f8. Then if you go to 4K, the pixel width is 2.5, but still the MTF of Nyquist is slightly above 0.45. And at 8K, you still have the same MTF at Nyquist, but now at a 1.25 pixel. So basically that scales nicely. The other thing though is if you close the lens, then there will be a point that the diffraction is limiting you're really limiting your resolution, because the cutoff frequency for the lens will be below Nyquist. Well, the point where your MTF is 0, I put there another formula in, and you can use it to calculate where that specific point is. Otto Schade, he did some investigations to, on one hand we have MTF, and that's an objective measure for expressing how much resolution you have at a given frequency. But his statement was that the squared MTF curve and then the integrated is how you perceive, is the perceived sharpness. So I did an integration up to 0.5 with those normalized spatial frequency, and 0.5 is just integrating up to Nyquist, because Nyquist is the frequency up to which you can reconstruct in a sensible manner your signal. And I called it sharpness dash MTF to make a distinction between sharpness as expressed into TV lines or circles per pixel width or line pairs per millimeter, and that's to make it more easy comparable. So here we have the normalized spatial frequency. It's the spatial frequency multiplied by the pixel width, or divided by the sample frequency. So in the camera you always find an optical low pass filter. It has a cosine characteristic with a 0, with no transfer at 1 over the pixel pitch. You have a pixel aperture that behaves as a sine x over x, also with a 0 in the transfer curve at 1 over h. And then finally you have your diffraction limited lens. So the good news of the story is that optical low pass filter and pixel aperture also degrade MTF, even though you don't want to have it degraded, but okay, that's life. So if you look at the overall MTF curve, it is just the multiplication of what the diffraction is doing, what the pixel aperture is doing, and what the optical low pass filter is doing. So if you look at that overall MTF formula, you see you only see the normalized frequency. There is no F number and no pixel pitch in it. It's only in the first part where the diffraction is in it. And you can, from the view of it, you can say that whenever the ratio between H and F is constant, as we did from going to 2K, 4K, 8K and opening the lens further, is constant, so that means that you have a constant MTF at the frequency you're looking at. Well, now, if you look in the 4K 2/3", 2.5 micron pixel, when you have an f4, then it means that the cut for the diffraction is somewhere at twice the optical sampling frequency. At 5.6, you have a 0, it stops at the sample frequency, and at f8, you won't get further than Nyquist. And preferably, you would not want to go below f8, because f8 just means that you kind of have an oversample system, because you won't resolve that what is offered in the scene. This graph is only for the diffraction, but as I said, you also have your optical low pass filter, you have your pixel aperture, and that changes the curves a little bit, but the zeros, there where the transfer is 0 stays the same. Using Schade you can calculate, but how much do I lose now in sharpness if I go down from f4, f5.6 to f8? Let's say at f4 you have 83%, so let's say, well, that's just 90% or 100%. At f8 you're down by even more than a half. So you really lose a lot of MTF in doing that. But of course, you can do aperture correction. Oh yeah. So, as I said, if you go from f8 to, for instance, f11 or f16, it means that you apply your imager as you oversample your image. And what that is doing, it won't help you in getting sharper images. It will only help you in reduced JS. It's a wrong photo. It says 1K, 4K, 2K. It's just a picture I got from one of the papers. In this case, it was a Centen conference, which nicely depicts what happens if you have an oversampled system without having any improvement in sharpness. You see, as I said, the jackies are reduced. Now, again, the sharpness. So, as stated, when the ratio of f number and pixel dimension is the same, it means that you have let's say, the same MTF utilization. Now, if you carefully look at the formula, because there's a minus sign for the 1.22, actually it's like this. If you scale with h over f, then the larger pixel will give you a better MTF, and that's because diffraction, you get a smaller line per millimeter, so you have less problems with your diffraction. F number, the same. When your F number gets smaller, then of course your MTF also increases. But of course, also that has its limitations. But you can translate the H, the pixel width, into diagonal divided by resolution. Now we come to depth of field, assuming that you frame the picture and view it in the same format. then actually it means lesser light, it means larger depth of field. But the scaling for depth of field is slightly different. First of all, it goes with 1 over the resolution squared times that ratio H over F, but in this case it's the other way around. So that must already give the feeling that that will go in the wrong direction. But I told you we were looking at a situation where the ratio between F and H is a constant. In that case you can preserve a signal to noise ratio at 60 dB. Then this simply states that if you go from 2K to 4K, that your depth of field goes down by a factor of 4. And if you would go from 2K to 16K, your depth of field would go down a factor of 16. In this plot, I showed how relatively depth of field changes, and in this case, I normalized it to when you would use an f8 in 4K, and the curves they stop at when the limitation reaches Nyquist. So the 8K can go to up to f.4. Of course, you can close the lens even further, but then it means that you enter into a region where you are below Nyquist, and that means that you won't resolve all the information that's in the image. For 4K, you can go up to f8 before reaching Nyquist, and in AC you even can go up to f16 before reaching Nyquist. But that I didn't put in the graph. So we have pixel size, we have f number, and we have resolution. And then the diagonal size is proportional to the resolution times the pixel width, and of course there's an aspect ratio into it. Sensitivity and sharpness, they scale comparable, so when sensitivity is kept the same, the signal to noise ratio is kept the same, then that means at least you have the same MTF at the frequency. But the depth of field just goes the other way around. Here it is shown in a table. Green means it's okay. Red means you're in the danger zone. Of course, this is from a perspective where depth of field can change fast, where focus has to be done fast. So it's in live sports. It's not in drama. I think in drama the depth of field of 32 millimeter would be really, really green. And then, of course, in the lower side, you see the red part means that you have to apply noise reduction, otherwise you won't get the performance you need. Well, so the good news, yes, you can scale the pixels in either 11 millimeter or 44 millimeter. You can make it smaller. You only have to open up the lens, and by doing that, you will have the same MTF at Nyquist. But the bad news is that when you go up in resolution, the depth of field goes down dramatically, especially in sports and live, fast moving. Fast focusing is getting difficult. And so in 2K, when you say you have to give a depth of field, then in 4K, it goes down by a factor of 4, and in 8K, a factor of 16. And in 44 millimeter, it's even more, but of course, everybody knows that when you go to a large image of 4 diagonal, get a smaller depth of field, because that's what everybody likes when you go for drama. So what can one do for sports? You can accept more noise in the black. Means more read noise, more shot noise. If you do that, then you're allowed to close the lens further. That means lesser photons on the pixel, 6 dB per f-stop, and the signal to noise reduces by 6 f-stop. Sharpness reduces also, and the diffraction cut frequency halves per 2 f-stops. But of course, sharpness can be enhanced. You increase the noise again, and the noise reducer has to do more. But when you open up the lens such that it's close to Nyquist or below, the part between the cut frequency and Nyquist, you cannot enhance anymore because there is no signal. So I guess that practically it will stop at Nyquist and that's it, unless you just like the non-jagged images better. And that's to be continued. Questions?
What about the sweet spot of the lens, where the side elaborations on the one side meet the diffraction on the other side, and you have an ideal f-stop?
You mean if you go from the center to outward the images?
Well, typically for a 2/3 inch lens, the side elaborations will hit the curve.
Yeah, okay. Yeah. The point is, the formula is just a theoretical formula, and that's not, in the end, that's not how lenses really behave. But it was an intention to see how, in a simplified fashion, scaling would work, and whether it would bring you in a danger zone. But of course, if you have the 2/3 lenses, I think they are usable up to, let's say, maybe 2.8, 2.0, and if you go below that, then you get all the distortions and all the things that will reduce MTF further. So there's not, I don't think that there's a real need to use it in that area. So that practically even means that you have a even smaller region for usage of the lens. Yeah.
So 3,000 photons, we're talking about on a particular building site?
Yes. Low, eh? It's a low number, eh?
It's a low number.
And great images.
But the next question is, how many bits per pixel, how many bits per photon do we really need if we only have 3,000 photons to count? You can count the photons.
Yes, that's the nice. Basically, there are you have the photons, and the photons get converted into electrons. And just as there are 1, 2, 3, 4, 5 photons, there are 1, 2, 3, 4, 5 electrons. There are now half electrons. So basically, the pixel is a quantizer. One in steps of one unit, and the unit is then 1 electron or 1 photon. And yes, you could argue, what is the need to have 16-bit conversion if you only have 3,000 photons and so even lesser electrons? And I fully agree with you. If you take the 10 bits, then you go to up to 1,000 electrons. If you have 12 bits, then you go to 4,000 electrons. So 14 bits, what is it then? Then you get something like 16,000, and that will be more sufficient. But you know how it is? We are technical guys, and from a technical point, you can argue something. But the outside world is unfortunately also about emotion, and people like 14 better than 16. It's the same discussion with high dynamic range. Yeah, but Peter, you cannot put all those 4,000, 10,000 plugs in 10-bit. Yes, we can. Would 12-bit be more preferable? Yes, of course. Would 16-bit even be more preferable? Yes, of course. But you can do it with 10 bits. There are also elements in it that help you. As I said, you have shot noise. Shot noise means you dither your signal. And that shot noise also helps you in, even if you have lesser bits to show the signal, your eye will average the dithering because of the noise, which is by nature, you cannot do anything about it, added to it. Sorry, I got carried away, but...
Any other questions?